to thinking about non-Euclidean geometry. Can anyone look at this video?
Yeah, I think they can. I'll keep updating in the forum under my post.
But any people who aren't in the forum, who aren't on the OWL side of this class,
yeah, as long as they can go on to the YouTube channel of mine.
Oh, okay.
Yeah.
I just got a message from somebody about it. That person's not on the OWL side.
No.
Someone found you on YouTube.
Pardon?
Like somebody found your video on YouTube.
Well, there are a couple of videos of mine on YouTube. So are any number of cats.
So that's a good thing.
It's
good company.
Yeah. And yes, I'm up there with the cat video. But except for these, one was a lecture on general relativity that I already mentioned to you, and then the other thing I know about of mine that's on YouTube is a talk I gave at a conference on metaphysics in science that we had at Weston 2 years ago, a year and a half ago. I don't know if you find that interesting or not. I mean, not particularly my talk, but the conference was on metaphysics within physics. So it's a lot of interesting talk, if you're interested in that sort of thing. So anyway, as I was saying, if you understood everything I was saying last time, then we're kind of at the point where we can think about what all this has to do with curved space-time. I was mentioning at the last point, well, we usually think of these examples of curved space when people try to explain what Einstein's theory was about. But you really have to think about curved space-time and the connection between gravity and inertia to really get the point of general relativity. So, does anyone have any questions about that? It's kind of like a criterion of identity, in the sense that, what are the criteria, in the sense of, when we were thinking about, say, inertial frames, what are the criteria you can use for being in an inertial frame, right? Well, in the Newtonian case, we said that every acceleration corresponds with a force. Every force corresponds with an equal and opposite reaction. If those things aren't true, you're not in an inertial frame. Right? So you have centrifugal forces, they don't have an equal and opposite reaction. So that's the frame in which they appear isn't an inertial frame. Right? We just go back even further and think of the Aristotelian idea, right? If you were to shoot a projectile in opposite directions, east and west, if they go equal distances, that means the Earth is at rest. But then Galileo teaches you, well, that would still happen even if you were on a moving ship. So that's not a good criterion of being at rest, right? It's not a criterion that identifies the state of being at rest in the universe, right? It only tells you whether you're in a uniform frame of reference, right? A uniformly moving frame of reference, excuse me. In other words, an inertial frame. And similarly, then Einstein said, well, here's the criterion. The Michelson-Morley experiment coming out null, that should have been a criterion of being at rest in the ether. Right? But it turns out that it works in any inertial frame. Right? If it works in one frame, it will work in a frame that's moving uniformly relative to that frame. So the idea that light takes the same amount of time to travel equal distances in any direction is a criterion of being in an inertial frame, not of being at rest in the ether. So now we've got to this point of thinking about inertial frames in this radically new way that Einstein suggests, that if you could at least on a small scale, right, you could be in a sort of frame of reference that seems inertial because no forces appear to be acting on anything. So you're satisfying the criterion of being in an inertial frame. And yet, you're not, because you're falling in a gravitational field. Well, Einstein says the criteria now start to be ambiguous. The criteria for being in an inertial frame, therefore, are ambiguous, right? Or take the opposite example, right, where it's at rest in a standing gravitational field, right? Is this the criterion, the fact that you feel your weight and you drop a ball and it falls at 9.8 meters per second, that's not a criterion of being at rest in that gravitational field. It could equally be a criterion for being in an accelerating frame of reference in the opposite direction. So what do you do with this fact that the idea of an inertial frame is an ambiguous one now? Well, there's a kind of, Einstein had a kind of circuitous route to this understanding that he had of this. It starts with this idea of a rotating disk. So suppose you do have a rotating disk, right? If you have a normal non-rotating disk and you measure the radius and the circumference, right? The ratio between the radius and the circumference is 2 pi, right? The circumference is 2 pi times the radius. Just for example, or you could think about the area, right? The area is pi r squared. But the circumference makes the example easier. You can just ask yourself, if I'm standing here measuring with a little measuring rod, right, and I walk around and measure the whole circumference, I get a certain value for the radius, for the circumference, and I also have a value for the radius. But if the disk is rotating, then the outer part of the disk is necessarily rotating faster than the inner part, right? Because, well, the whole thing is rigidly rotating, so it might sound like it doesn't make sense. But if you have a particle moving here, attached to this part of the disk, it's moving faster if it's at the edge, because it's moving through a greater arc in the same amount of time. Now, if you throw special relativity into this mix now, an object at the edge of the disk moving faster than a seemingly identical object at the center of the disk is going to appear to contract. That would mean that it takes more of these same measuring rods to go all the way around the circumference. So the circumference measured in these units would seem like it's bigger than 2 pi r, right? Because it takes more of the same measuring stick to make it all the way around, because the measuring stick is contracted. What can you conclude from this? It's not clear how much you can conclude from this. It's really more like a heuristic, I think, than sort of a suggested example than something you can logically deduce anything from. I mean, well, it's not that you can't logically deduce anything. It just doesn't logically lead you to a new theory. It just, what are the logical implications of this thought experiment? Well, the one that you can really point to is you actually have a choice here, according to Einstein, about how to think of the reference frame. Is the reference frame rotating? Well, if it's rotating, of course you would expect the circumference is bigger than 2 pi times the radius, because the rod is shrinking. But you could equally say the reference frame is at rest, and a non-Euclidean geometry applies. So it throws in the idea of connecting the different states of different hypotheses about what the frame is doing, what the frame of reference is doing, and different geometrical structures, because Euclidean geometry fails if the ratio between the circumference and the diameter isn't 2 pi, sorry, isn't pi. Right? So you can say, well, either I'm rotating or Euclidean geometry is wrong. Which is kind of analogous to this case where you say, well, either there's a gravitational field or my whole box is accelerating this way. Or either I'm falling in a gravitational field or there's no forces of any kind acting on me at all. Right? Either no forces are acting or just gravity is acting. It's like that. Except in this case, there's this suggestion that you can think of different geometries as connected with this different choice of frames of reference. Because it follows that, well, I'm either at rest in a non-Euclidean, on a non-Euclidean disk, or I'm on a rotating disk and special relativity is changing the apparent relationship between the circumference and the radius. But see, that's, in a sense, has nothing to do with general relativity, because it doesn't tell you anything about a new space-time structure. I mean, this example, it just tells you that there could be a circumstance in which a non-Euclidean geometry would be an equally good explanation for what seems like a change in the state of the motion of the reference frame. See what I mean? So it's highly suggestive, although it's not clear how you would get from that to general relativity. But there is once you have the idea in your mind that there is a connection between the state of motion of the reference frame and geometry, then it becomes possible, I guess, I mean, this is all more or less trying to reconstruct what Einstein was thinking. Even though we do know a lot about it, it's still not exactly clear. It's possible to think your way from these examples, once you have the idea of a non-Euclidean geometry, to a non-Euclidean geometry of space-time. So now to do that, you really should stop me if you're not following. Because why not? So if I can think about non-Euclidean geometry for a while, what are the characteristics of the freely falling trajectory? Well, we already talked about some of them, right? We know that in free fall, at least over a small enough area, right, objects that are falling in a gravitational field that's more or less homogeneous, right? Because at least it looks homogeneous over a small scale, right? Gravity seems to be acting on them all in the same way. So a bunch of objects in free fall will more or less move parallel to one another. Remember, I was just saying this last time. If you look at a big enough area, right, everything's falling toward the center of the Earth, right? So of course, if you look at a very large falling box, right, you might actually detect the inhomogeneity, namely doing all these things are not falling in parallel lines, they're falling in lines that converge on the center of the Earth. Right? Yeah.
Yeah, sorry, I was only wondering if the space shape is big enough and with enough mass, then I think in that scenario the planet would fall into that space shape, which means vice versa to the situation. And in that situation, I think it would be a similar question to ask whether if the planet is falling into the center of that spaceship, or because I don't know. I'm just thinking because the spaceship is splitting off, so the planet could also be falling into the several spots on the spaceship. Which one would be more possible?
Oh, I mean, that's a general principle, right? That's
Yeah.
true in Newtonian gravity generally, right? I mean, it doesn't have to be, you don't have to think about a big spaceship. If you think of the Earth attracting a golf ball, right? It's still true that if you were to measure with great precision, yes, the Earth is being pulled toward the golf ball, and the golf ball is being pulled toward the Earth, and they're equally and oppositely attracting one another. It's just that the mass of the Earth is so overwhelmingly great compared to the golf ball that the center of mass of the two of them is indistinguishable from the center of the Earth, right? Whereas if you had a gigantic spaceship, well then maybe, yes. If people from Earth could, if people from some other space came, suppose they had some thing that they built that actually had a mass something like the mass of the Earth. Right? It would be like us taking a very massive spaceship out to some asteroid that's, only weighs a few tons. Right? So that's all true. I mean, it's just a question of how big does the frame of reference you're thinking of have to be in order for the inhomogeneity of the gravitational field to appear. I mean, I'm just drawing an exaggerated diagram because if you're just looking at, a tiny space shuttle, which is like a dot compared to the size of the Earth, right? You're not going to notice something at the front of the space shuttle and the back of the space shuttle converging on the center of the Earth. It's going to look parallel, right? Or you think of that other thing, like this whole system of Saturn and its moons, even though it's a gigantic planet with a huge system of, I don't even know how many satellites it has. Does anybody know? It's a whole bunch, right? That whole system is so tiny compared to the distance of the sun that the inhomogeneity of the sun's gravitational field is insignificant, right? It's not pulling them all in parallel lines, it's pulling them all in lines that converge on the center of the Earth. But who can tell, right? Even for a large system like Saturn and its moon. Or the solar system, right? It's being pulled towards something. But in so nearly parallel lines that it doesn't matter. So if you think of what's happening in Newtonian gravity when two objects fall to the center of the Earth that you dropped. Well, if you look at sort of the world tube of the Earth, just assume it's not accelerating or anything. Forget about its motion around the sun. Or you could say, well, this is its actual path in space-time around the sun, but we're just looking at a little segment of it that looks straight. So here are these two objects. The principle of inertia says they will move uniformly in a straight line in parallel lines, right? If they are dropped with identical velocities. What happens is the Earth is pulling them in, so their actual paths look like this, right? And they come down and land on the Earth, right, at different spots. Now these trajectories are their inertial paths, right? If they were moving inertially. So these are the straight lines of space-time, correct? Because that's what an inertially moving body does. It moves on a straight line of space-time. So now bring in this argument and say, well, actually, this argument tells you that as far as satisfying the empirical criteria goes, the observer in this path can claim to be moving inertially. Yes? your observer moving in this path says, well, as far as I can tell, by local criteria for identity of an inertial frame, I appear to be in an inertial frame. Now, of course, this observer can say the same thing. Right? I appear to be moving in an inertial frame. Now, this observer can say, well, I'm moving in an inertial frame. Obviously, you are not. You are accelerating toward me. Right? And of course, the other observer can say the same thing. I am moving in an inertial path. You are accelerating toward me. Go away. Obviously, forgot about that court order. Now, the thing is, if you lack empirical criteria for saying this one's not an inertially moving body, then you have to consider the hypothesis that, or let's say the possibility, that this is an inertially moving body. And that bodies that are falling in a gravitational field are as good as inertially moving bodies. They satisfy all the same criteria. It's kind of like the situation when you say, well, bodies that satisfy the Michelson-Morley experiment are as good as bodies that rest in the ether, right? Laboratories that satisfy where the Michelson-Morley experiment comes out null are as good as laboratories that are rest in the ether. In fact, nobody can tell which is which. Therefore, you have to, this doesn't quite make sense until you abandon the idea of absolute simultaneity. Right? Now, this idea doesn't quite make sense either, until you have to abandon something else. But what is it? Well, now, go back to sort of think about ordinary non-Euclidean geometry on a surface, like the surface of the Earth. Now, suppose you didn't know that the Earth was a sphere, and you have two observers who've moved perpendicularly from the equator, which they just think is a line that goes straight from east to west, which it is, of course. But they both move perpendicularly toward the equator with an agreement that they're both going to use, say, I don't know, an inertial guidance system to make sure they don't turn left or right, but stay parallel and stay away from each other and maintain the same distance. Right? Now, if they were moving in a plane and they moved at some, obviously, if they move perpendicularly to some given line, Euclid's fifth postulate tells you they'll never meet, right? Whereas if one of them slightly deviates from perpendicular, then eventually they will meet. I mean, if it deviates on the side of less than 90 degrees on this side, right? They're bound to meet. They must meet. And of course, they can only meet once because it's Euclidean geometry, and if they're moving in straight lines, their paths can cross, but never again. So what would you say if they both follow the same instructions and they start off in parallel directions, but then they find themselves mysteriously converging, each one complaining that the other one is violating this agreement they had to stay away from each other? Not only that, but each one is moving in a straight line. Their paths cross, but then they diverge again, right, on the other side, right, coming down on this side of the Earth. And after a while, they start to feel like, that whole chapter of their life is over, they're never going to meet again. But then they start converging again and meet on the South Pole. Now you could say, well, there's a couple of different ways of thinking about this, right? One is, well, there's some mysterious force, right? Like, if doesn't have to be a really mysterious force. It could just be, well, one of them is actually deliberately deviating from the straight line. Right? So one of them can say, you're deliberately deviating from the straight line in order to converge on me. And the other one can say the same thing. And the other way of looking at it is, well, neither one of us is deviating from the straight line. But as in those other cases, right, we were making a mistake. We thought we were on a plane. In fact, we're on a non-Euclidean surface. And because a non-Euclidean surface is a place where these things can just happen. Two straight lines that start off perpendicular to the same straight line can converge on one another. And having met once and separated, they can perfectly well connect up again. They can intersect twice. This is one of those things that is Kant's favorite example of something you know is true in geometry a priori, that two lines can't enclose a space. In space, of course, Kant knew as well as the next person that on a sphere, yes, two lines can enclose a space, if you call those lines, because they can meet twice if they're the straight lines of a sphere, right? The great circles, the lines of longitude, all meet twice. But in space, when two lines meet, they just keep diverging. So once you understand how, if you remember our previous discussions, how space can be non-Euclidean just as much as a surface can, and you could say, well, in space, this could happen if it was a spherically curved space, right? That two lines that met once could diverge for a while and then start to converge. And you would say, well, actually nobody was doing anything but following a straight line, but it turns out that the surface we're crawling on is non-Euclidean. But the funny thing is that nobody really, I think I might have mentioned the examples, right? Looking at very large triangles, optical triangles, like taking the parallax of very distant stars and seeing, there's no observable deviation from Euclidean geometry in space, even on these huge scales, right? Whatever deviation there is from Euclidean geometry is too small to notice. Nobody ever really did anything with the idea of non-Euclidean space, as far as empirical science goes. I mean, mathematicians play with it, but nobody found a reason to think of space as being non-Euclidean. So mathematicians played with it in the sense of finding different non-Euclidean geometries, trying to figure out whether you could still do Newtonian mechanics in a non-Euclidean space. Apparently you can. But nobody needed to. There was no reason in physics to think that space was curved. So really, even with Einstein, it wasn't obvious that there was a reason to think that space was curved. But this example shows you a reason to think of space-time as curved. Because if you remember, well, the paths of inertially moving bodies are the straight lines of space-time. But if the paths of falling bodies deserve to be thought of as the straight lines of space, of space-time, if they're equivalent to inertial paths, they deserve to be thought of as the geodesic motions of space-time, then how can you interpret this picture? Well, you have geodesic motions that converge on one another, that accelerate toward one another. You have observers moving on geodesic paths, each of which looks at the other and says, that one's not moving on a geodesic, but I am. I know I'm not because I do all these experiments and I can tell I'm in an inertial frame. Right? But obviously that other person is accelerating toward me. And that's exactly analogous to this case, when you say, well, that other person is accelerating toward me, right? Because this is a non-uniform convergence, right? It's different from the case, from this case, right? Because if they really were converging on one another in a plane, they would converge uniformly, and then they'd separate uniformly and never converge again. But here, the convergence is, so to speak, accelerating. Well, that's what's happening here. You have two observers falling in a gravitational field. Each one thinks they're moving inertially and thinks the other one is accelerating. But really, locally, both of them can satisfy all experimental tests of being moving inertially. But of course, if this is the case, then you necessarily, in order to call both of those inertial, right? In other words, in order to call both of these paths straight lines of space-time, you have to accept that space-time is like a non-Euclidean space. A space in which the straight lines can converge and can converge more than once. Straight lines can accelerate toward one another. You can kind of imagine a case where they kept meeting, right? If you this is hard to do because of the air resistance, but if you had a perfect vacuum and you had a sort of a tunnel through the earth and people sort of jumped into it from opposite ends, right? They fall on their geodesic paths and they go all the way up on the other side, somehow without losing any motion, right? They cross in the middle and they go up, each one goes to the diametrically opposite point, then they fall down again and cross paths again, right? And in space-time, that would kind of look like, again, ignoring the rotation of the Earth, right? That would be like falling to the center, here's the Earth's world tube, right? Fall to the center of the Earth, rise up on the other side, fall back again, right? And so they'd be meeting and then meeting again. And that would be the space-time interpretation of two people who fall through the middle of the Earth and see each other and then pass each other by. But the basic idea is, well, if I start with the idea that I'm in an inertial frame, then I construct an inertial frame in which I'm at rest, say, on whatever axis I prefer, right? I say this is an inertial frame, and I'm standing here at the origin. And I look at you, and I think, well, here in my inertial frame, you're on some kind of accelerating frame. You're accelerating away from me or accelerating towards me, whatever you're doing. If we're both falling toward the same planet, then we're accelerating toward one another. But then, of course, you can draw the same diagram, right? And say, well, I'm at rest in this inertial frame, and there you go, in an accelerating frame of reference. But that's how you tell if those are both geodesic lines. I don't know if I used the word before, I think I did. When I was first talking about space-time, geodesic line meaning just the straightest line you can draw in whatever space you're in. That's how you can tell you're in a non-Euclidean space. So, for example, you draw your little frame of reference here, right? Here's your little coordinate grid. Right, so well, hey, I'm in a flat space, because that's my little coordinate system, right? Now, here you are in your coordinate system, right? And you draw a little grid for yourself. Right? But our coordinate systems are kind of disoriented with respect to one another. We might eventually figure out that it's because our coordinate systems lie on the curved surface of the Earth. Right? There isn't a way for me to extend my coordinate system so that yours is sort of included in it. Whereas if they really were on the surface of this blackboard, right, I draw a coordinate system here, you draw one way over here, right? Because the blackboard is not only homogeneous but flat, if I make my coordinate system large enough, right, I extend it all the way over to here, right, then I can say, oh yes, well your coordinate system is indeed a flat coordinate system in my coordinate system. It's just that you've got the axes oriented a little bit differently. I can always just turn them this way. And so this is the idea that space has a symmetry, right? Has a Euclidean symmetry because it means, well, without sort of leaving the blackboard or changing anything really significant, I can just sort of, I can turn the coordinate system, I can rotate it in either of two directions, and I can move it up and down in either of two directions, or any combination of the two. And if I know, for example, the length of this hypotenuse in my coordinate system, it's not going to look different to you. It might be more complex to calculate because it's nice and easy here, because here in my coordinate system, right, the two sides are just on the axes, so it's really easy for me to compute Pythagoras' theorem. You might find it convenient to adopt my coordinate system just so that you could compute it. But if you do it, if you took the same, an equal length in your coordinate system, it'll still, the fact that you turn the coordinates one way or another won't change what's really important in Euclidean plane geometry, which is the lengths and the angles, right? It's just a question of making, changing your coordinate system slightly. Whereas if we were on a curved surface, you just couldn't do that. Because when you if I extend my coordinate system on the Earth, well, so to speak, it leaves the Earth, right? It's only tangent to the Earth. It looked like my coordinate system could lay flat on the Earth because it's small compared to the Earth. Right? It's like you have a curved surface that you want to cover it with tiles, right? Well, if you use tiles that are large with respect to the surface, then it'll be hard to make them sit down on the surface. But if you make them small enough, they'll fit. But if you want it to fit exactly, well, if the surface is really variable, then you've got to make them infinitely small. I kind of like this example because one of the most annoying features of contemporary life, so I'm glad to be able to do something useful with it. If you know how if you buy an apple and there's a sticker stuck to it, right? I find that really annoying. When you get old and cranky, right? These little things bug you. Luckily, it's a nice illustration of the non-Euclidean surface, because you can say it's obvious there's a kind of optimization problem there, right? If they made them too small for the checkout person to read, or maybe you were going to read it too if it's not obvious what kind of apple this is or whatever, right? It's got a number and the name of the apple variety, right? And it kind of lies there on the surface of the apple because over a small area, at that part of the apple, right, the apple is kind of close to being flat, so you can stick it there. But of course, if you made the sticker too big, then you couldn't stick it on there without a bunch of wrinkles. right? Or if you put it in the wrong place of the apple, like it's a red delicious and it has this kind of, well, they all have some kind of, indentation, right? At the stem and at the bottom, right? And, even this sticker, you wouldn't want to put it here if it's one of those really pointy, relatively pointy parts of certain apples, right? So the curvature of this surface varies, right? Here it's kind of close to being flat. Down here it curves a lot, so you can't make the sticker sit on it. You have to use smaller stickers, right? The larger you make the sticker, the harder it is to stick there, right? Whereas on this surface on a flat surface, right? You take a sticker that fits here, you could make it as large as the whole surface and it would still fit. Right? So this is kind of analogous to the cases of relativity that we talked about before, right? Where the question is, you have your own frame of reference where you apply a certain criterion of identity, and you can ask the question, well, what about that other frame of reference? Does it satisfy the same criteria? Right? So Aristotle says, look, this frame of reference is really at rest. Galileo says, well, my moving frame of reference satisfies the same criteria, so you can't really be at rest. Or no one of us is more at rest than the other. Or here's a laboratory moving through space where the Nicholson-Morley experiment is null. Well, here's another one that's moving relatively. They both satisfy the criteria. You have to find what is the bigger picture into which these opposing views fit. So when it comes to curvature, you can say, well, if I try to extend my plane and I say, look, where I am is perpendicular. If you stand vertically here, if you build put up a flagpole, it's perpendicular to the surface. And the other person says, well, no, actually, this is perpendicular to the surface. Well, perpendicular lines to the same surface should be parallel, unless it's not a flat surface. If it's not a flat surface, then perpendicular lines won't be parallel. And you can't extend your frame of reference to a larger frame of reference that includes the other one. Well, that's the same as this case with the two freely falling observers. Right? In special relativity, say, well, if my frame of reference satisfies the criteria for being an inertial frame, and yours does too, then your motion will look like an inertial frame in my frame of reference, and mine will look like an inertial motion in your frame of reference. And we could agree on a common frame of reference in which we're both moving inertially. But if the path of a falling body is as good as an inertial motion, then I can't find a common frame in which the two frames of reference are both inertial. And that's essentially what makes this large picture of a non-Euclidean space-time geometry into a kind of coherent picture into which these seemingly opposed perspectives both fit. But see, I started talking about this last time. In a way, this has nothing to do with special relativity. In a way, you could say, well, if Newton knew how to deal with non-Euclidean geometry in 4 dimensions, he could have said this, because he already knew that you can't tell a freely falling system from an inertial frame. Maybe if somebody had had all this geometry at their disposal earlier, philosophers of physics have written a lot of papers on this. Like, well, suppose there had been somebody who suppose knew all this geometry, what would he do? Why wouldn't he just take his theory of gravity and say, this theory is the theory of a non-Euclidean space-time? It's just that he didn't know about, he wouldn't have any reason, based on what he knew, to have special relativity. So it would be like saying something like the following. According to Newton, you have planes of absolute simultaneity, right? Because he just took it for granted that you could. His theory of gravity assumes this, right? There are planes of, that space-time is decomposable into this series of spaces at different times. And each one of these planes is flat. Space is always flat. But space-time, you could say, just in purely Newtonian terms, space-time is flat because even with Newton's theory of gravity, you have two falling observers. You can't tell which one of them is moving inertially. Each one of them can claim to be the inertial observer. So you could say, even in a kind of Newtonian, with Newtonian time, in Newtonian physics, you could say, based on Newton's theory of gravity alone, I might have thought of representing space-time as curved. As a matter of fact, nobody thought of this theory until after Einstein came up with general relativity. A French mathematician named Cartan came up with the idea that actually you could just make it, you could think of geometry, of curved space-time geometry, even in the Newtonian context. You can say the Newtonian theory of gravity is a theory of curved space-time geometry. Even though spatial geometry is flat, space-time geometry is curved. We could have done it that way. Nobody ever did, nobody had a reason to. Many people think, this is how, this is how I was taught. This is actually a simpler and nicer way to think about Newtonian gravitation. But the point isn't the historical speculation, you know, what if we can do more differential geometry? The point is to realize the logical independence of two things. On the one hand, there's this view of electricity and magnetism that leads to special relativity and the dissolution of this idea of absolute time. On the other hand, there's this notion of getting rid of undermining the idea of an inertial frame, because gravity has this peculiar feature of making it impossible for you to tell if you're in an inertial frame. And that leads to the idea of curved space-time. So special relativity, electrodynamics leads to this idea of space-time without simultaneity, right? With a metric instead of simultaneity, right? With the light cones instead of simultaneity plane. And gravitation leads to this idea of curved space-time, and they're completely independent ideas. It's just that in the actual order of history, it happened the other way. I mean, it happened in the way that it actually happened. Unfortunately, we don't have time to stay for questions, but feel free to send me any if you have any last-minute questions about your essay, which is due on Friday. If you've got one, yeah. If you send it on after class on Friday, then you might have to send it to me.
I can see it now.
Yeah.
It's due on Friday?
Yeah, it's due on Friday.
Oh, okay.
I just announced it at the end of class
Yeah.
last time that
If
if you want to take it back and think about it.